everybody for coming to the seminar. Ahmet works mainly on matching. He is currently in Nazarbayev University in Kazakhstan. But if Juan remembers, we actually met Ahmet in 2019 in Stony Brook, and we had the conference dinner with Ahmet.
Yeah.
Yeah, and we are happy to have him present today. Thanks, Ahmet, and the floor is yours.
Yeah, thank you very much. I appreciate you, having me present my work. It's a great opportunity. I'm looking forward to hearing your comments, but I am also trying to sort of, share my screen as a full screen. If you give me a little bit of 30 seconds, I'll be done with it.
Okay.
Yeah, I apologize for this delay.
It's okay.
All right. All right, so can you all see now the slides as full screen?
No, we see some window with the files, not the slides. So it doesn't need to be full screen. I think the previous one was okay.
Okay. How about now?
No. Now we see a window trying to get closed, but it is not going down. No.
Let me just put everything down.
Yeah.
And put this up.
It looks, well, I think it's kind of a frozen screen trying to minimize itself, but it's frozen.
I am not sure why this is not happening.
So we can go to the first thing that you did, where we partially, now we can,
perfect.
Full screen, everything is working, perfect.
I'm sorry, I really apologize for this.
No, it's okay.
Somehow it takes some time. All right, again, thank you very much, everybody, for having me. This is a great opportunity. I am looking forward to hearing your comments and feedback. I want to point out that this is a work in progress, so just feel free to stop me at any point if you have any questions or you need me to clarify some things even more. Well, that being said, let me try to, let me start by telling you what I'm doing here. So as many of you might be familiar with, matching has many real-life applications, especially minute-one matching has a lot of real-life applications, such as labor markets, entry-level professional labor markets, such as medical residency matching or federal court clerkship in the US, or the college admissions and school choice problems. So these are the applications that one can think of as examples of minute-one matching market. So obviously, there's a huge literature in these markets. I'm not the first one, looking at these ones, but the extant literature regarding these markets supposes that the matchings take place simultaneously in a static fashion. However, in some of these markets, the matchings take place sequentially. For example, take the college admissions in the US. Most selective colleges offer early admissions and regular admissions, which sort of makes these college admissions inherently dynamic in the US. Similar patterns can be observed in some of the entry-level professional labor markets, more often in some of them the others, but we do observe sequential matchings in some of these entry-level professional labor markets as well. So motivating from this evidence in the real-life applications of minute-one matching markets, in this paper, I study minute-one matching markets in a dynamic framework with the following features. First, agents arrive to the market over time, and these arrivals are exogenously given. So this is to capture the idea that not every participant might be available to match at every time in a matching market. And also the arrivals are given exogenously. This again, could be thought of that the arrival decisions depend on some exogenous factors which are independent from the matching process itself. And the second feature, important feature of the model will be that the matchings that forms early on will not be able to get broken in subsequent matching markets. In other words, the matchings are irreversible. So another way of interpreting this assumption would be that suppose that there's a really high cost associated with breaking a match in subsequent matching markets, so that nobody is willing to do so. So everybody will anticipate that they don't want to break the match, they will not break the match later on, and they will form matches in earlier periods accordingly. So there are two parts to the paper. In the first part, I studied these matching markets with an exogenously given arrivals, but perhaps more realistic assumption would be to allow agents to choose when to join the market endogenously. So in the second part of the paper, I relax these exogenous arrival decisions and allow agents to endogenously decide when to join a matching market, and study the unraveling incentives provided by commonly used matching mechanisms, matching algorithms, known as deferred acceptance or Galian-Shapley algorithm. But I'm afraid for the interest of time, I'm not going to be able to go over the second part of the paper, but I will be happy to talk about it in case any of you would be interested in off the line. Well, let me try to give you the main insight, the main sort of behavior that mechanism that I'm going to focus on in this paper in one slide. I point to a novel strategic behavior that pertains only to dynamic many-to-one matching markets. That is, the site with many slots might use early matchings as a tool to manipulate the subsequent matching market in their favor. In the context of college admissions, let's say, just to fix the ideas, I'm going to use the language of college admissions, but you should think that the colleges can correspond to institutions such as hospitals or firms, and the students can correspond to interns or say workers, all right? So in the context of college admissions, this behavior could be the following. Colleges might find it profitable to sacrifice some seats to lower ranked students in early matching periods to be able to enroll even higher ranked students in the subsequent matching market. And this overall set of students could be preferred by those colleges to the students that they would have gotten in a static environment. I will show you this behavior in a very nice, with a very nice example. In fact, the example hopefully will convey the entire results that I'm going to provide today to you. So if you bear with me a little bit, this behavior will be more sort of apparent with the example that I will provide later on. Well, given that such a behavior arises in dynamic many-to-one matching markets, what I do here is first to provide a solution concept, a novel solution concept for dynamic many-to-one matching markets, so which I call as dynamic group stability. This dynamic group stability, you can think this as merging the dynamic stability that is introduced by Doval in 2017 in her journal paper with the standard group stability of many-to-one matching markets in static settings. I will be more specific about the solution concept as well later on. But introducing this solution concept, the next question that I ask in the paper is the following. So are there situations under which a dynamic many-to-one matching market can be simplified to a static many-to-one matching market? In other words, can I just behave as if the market is static and the matchings take place simultaneously, just like what the literature has been doing so far? So this is an important question because it will allow me to understand the situations where dynamics do versus do not play in a role. To motivate the second question, perhaps it would be useful to go back to the static environment. In a static setting, many-to-one matching markets do not have much novelty under a very common class of preferences, so-called as responsive preferences. So responsive preferences corresponds to the case that the preferences over sets of students for the colleges are consistent with the preferences over individual students, roughly. And I will be more specific about that as well. So under this set of preferences, one can think of a college with n separate slots as if it is n separate colleges with one slot and carry over the preferences carefully. And it turns out that this artificial one-to-one market will have a set of stable matching that is equivalent to the group stable matchings of the original many-to-one matching market. So so this is a useful trick to compute stability in a static environment under responsive preferences. So it would prove useful to know whether the same technical trick extends to a dynamic setting as well, so that we can use dynamic one-to-one matching markets as a tool to compute stability in our original dynamic many-to-one matching market as well. So these two questions are important, just like I was telling before, because it will allow us to simplify the problem somewhat into a lot simpler environment. But for the reason that I was talking in the previous slide, for this strategic manipulation that colleges might want to do, the answer to these questions is in general no, right? So when the answer is no to these two questions, what type of matchings should we expect in a given dynamic many-to-one matching market? So I'll provide some properties of the matchings that arises in a market which we cannot simplify to a static many-to-one or a dynamic one-to-one matching market. So these are the questions that I'm after in this paper. This for the first part of the paper, and let me try to give you simply. Let me try to briefly give you the results that I'm going to talk today. Like I was telling before, unless the strategic manipulation with the commitment that the colleges might want to do and is not ruled out, dynamic many-to-one matching problems cannot be reduced neither to static many-to-one matching markets nor to dynamic one-to-one markets. But then I will provide conditions, some sufficient conditions under which such a simplification is possible. First of all, the first condition is about the capacity constraint of the colleges. It essentially says that the colleges might find it profitable to commit to some lower ranked students, and this commitment is going to sort of induce a credible commitment in the subsequent matching market that tells that the colleges will not poach students from each other, and that heavily relies on the fact that the colleges have limited capacity. So simply, if the colleges were to have no capacity constraint, then such a behavior would not arise, and we could just rely on the outcome of the associated static many-to-one matching market. But the primary case of interest is the situation where the capacity constraint is binding. So when the capacity constraint is binding, I'm going to provide two classes of preferences under which I can still rely on the results of the associated static many-to-one matching market, which essentially will tell me that by looking at as if the market is static, although it was dynamic, I wouldn't lose actually nothing. First one is standard sort of acyclic preferences, which essentially corresponds to the case that we do not have any sets of colleges and sets of students where the preferences over each other is sort of reversed in a way that it forms a cycle. I will be more specific about this as well. So as long as the preferences do not exhibit any such cycles, again, the static version will work just fine. And the third and the last condition that I will provide is something new that I introduced in this paper, which is akin to the notion of mean preservance spread. So responsive preferences does not really tell us how we rank some sets of students. And I do classify these sets of students which responsive preferences stay silent into two different subsets as average preferences and extreme preferences. Again, I will be more specific about it. And it turns out that whether the colleges have average versus extreme preferences plays a crucial role. That whether these colleges might want to manipulate the subsequent matching market or not. All right, I'll be more specific about these results hopefully right after the example. But let me then go forward and tell you one more result, hopefully, if time allows, that I'm going to talk about. So the first part is the part that I construct conditions under which I can rely on the results of the associated static many-to-one matching market. But then the answer will be no sometimes. If none of these conditions, if all of these conditions arise at the same time, then then the colleges might find it profitable to do this manipulation. Then what kind of matching should we expect in such an environment if we cannot rely on the results of the associated static many-to-one matching market? So it turns out that if that is the case, the students who are admitted in early periods who are admitted in early periods are lower ranked students for that particular college as compared to the students who are admitted in the subsequent matching market. And this essentially is, so this is good because we have similar pattern in the US college admission system as well, which I will talk more specifically later on as well. And I have more results about the endogenous arrival for the second part, but for the interest of time, I'm going to skip that for now, but I'll be happy to talk about it if anybody has any questions on that. So if you don't have any questions, I'm going to mention literature very briefly and start with the model. Okay, so I believe no questions at this point. So this paper contributes to dynamic matching environment. There's a growing dynamic matching literature, but to the best of my knowledge, almost all of them focus on markets where they are one-to-one matching markets. The first strand of the literature, introduces solution concept for a dynamic one-to-one matching markets, and investigates the dynamically stable matchings in their own environment. And I provide a solution concept for dynamic one-to-one matching markets, and that's how I contribute to the first strand of the literature that I marked there as 1I. The second strand sort of looks at the optimality properties of commonly used matching algorithms in a dynamic framework again, but for one-to-one matching markets. So I do look at the commonly used in the second part of the paper. I do look at some of these commonly used matching algorithms and try to understand the incentives to unravel under these various matching algorithms. So that's how I contribute to the second strand. And obviously, I am sort of with this paper identifying the matching markets which are fragile to unraveling and which are fragile to unraveling. That's how I contribute to the last strand of the literature as well. So let me start introducing the model, unless you have any questions so far. Okay. I'll have only two periods, which is enough to sort of convey the message, but the results can extend to finitely many periods. So I'm going to have colleges and students. Like I said before, I will use the language of college admissions, but you can think these colleges as institutions and the students as workers or whoever is on the other side of the market. So each college is constrained with a capacity, which I call as quota, and colleges will be in the market from the very beginning. So each college is in the market from period 1, and they join for both period one matching arrivals are given exogenously in this part of the paper. Let's talk about the preferences. I want to first talk about the preferences over the students. Since the students will be matching to single colleges, students will simply have preferences over the colleges. But the colleges will be matching with sets of subsets of students, so then they will have preferences over sets of students. And I'm going to suppose from the very beginning that the colleges have responsive preferences. And let me tell you what responsive preferences means that. So responsive preferences essentially corresponds to the idea that whether a student is acceptable or not, or the relative desirability of two students does not depend on who else is already in class. So, formally, if a student is individually preferred to be, preferred to a null set, better than nothing at all, then adding this student to any subset is better than not adding at all. And same idea sort of extends to the case where a student S, let's say, is preferred to student S prime. If and only if adding this student S to any subsets of students is preferred to add in S prime to the same subset. Okay, so as an example, the utility function that is additively separable in the students would represent responsive preferences. This is just one example to illustrate the idea of responsive preferences. Okay, so now that we know what, now that we are given with the environment here, let me try to sort of illustrate what a dynamic matching looks like here. So where we have two periods and matchings might form in either of these periods, right? So I'm going to first define a T period matching, which is simply a mapping from the set of students who are sort of at the market at the time at period T to the set of colleges union the null set, which essentially reflects the idea of staying single. And by definition, the colleges will not be mapped more than their capacity. Okay, so given that we have defined the T period matching, I can define first period matching and the second period matching. Notice that there is something that is conflicting with the irreversibility assumption that I had in the beginning, right? So with this definition, a student can be matched in the first period to some college and in the second period to another college with just this definition of period T matching. So I'm going to call a pair of a first period matching and the second period matching feasible as long as a student who is mapped to a college in the first period will be mapped to exactly the same college in the second period as well. So that will sort of guarantee that the matches will be irreversible. Okay, so now that we know what a feasible matching as well, a couple of notations. So notice that we're going to have a set of first period matchings and a set of second period matchings, but the feasible set of second period matchings will be contingent upon the first period matching. Okay, given a first period matching, now I have a set of feasible second period matchings, which is a function of the first period match. All right, so you might think that, given the first period matching and the second period matching, this should be enough to define a dynamic matching, but it is not going to suffice because the agents of the first period must have a theory about what will happen in the subsequent matching market if they were to deviate from this particular M1 to something else. Okay, so for that, I'm going to define a contingent matching plan, which maps every first period matching to a feasible second period matching. Right, and I'm going to denote that contingent matching plan with this cap mu. Well, given that the contingent matching plan is also there, now I define a dynamic matching as the pair of a first period matching and a contingent matching plan, which maps every possible first period matching to a second period matching. So now in this dynamic matching, the agents of the first period will have a theory about the expected second period matching, which will be given by mu if they were to deviate. All right, so this now defines the dynamic matching in our environment. Now that we have talked about matching as the matching as well, dynamic matching in our environment, let me try to give you the solution concept, the dynamic group stability. But for that, let me start with a simple stability in the static setting with an example, just to illustrate the idea. Let's say that we have two colleges and two students, and simply each college has capacity 1, so it's a one-to-one. It's a one-to-one market. And suppose that every college prefers student 1 to student 2, but each college prefers to be matched as opposed to staying unmatched. And each student prefers college 1 to college 2. And just like the colleges, each student also wants to be matched as opposed to staying unmatched. All right. So in this environment, the following matching, where college 1 matches with student 2 and college 2 matches with student 1, will not be a stable matching because college 1 and student 1 prefers each other and they're not matched. So they can block this match, right? On the other hand, the matching that college 1 and college 2, college 1 and student 1 and college 2 and student 2 are partnered will be a stable matching. So that's the stability, the stability in a static environment, right? But notice that this is the stability that is defined for one-to-one matching markets. So we're looking at only pair of agents who would like to be together, as opposed to the partners that they get under some matching. But if we were to look at the many-to-one matching market, these blocking coalitions can include a college and multiple students, perhaps multiple colleges and multiple students. Hence, the notion of group stability follows in the static environment, which essentially asks for a matching to be immune to any size of blocking coalitions. Right? So that's the group stability of the static environment, and we want to extend this group stability to our environment, to a dynamic setting now. Which, notice that in our environment, the matchings will be formed in the first period and in the second period, which essentially will sort of require us to check blocking coalitions at every period. Right? So roughly, let me informally try to give you what dynamic group stability is. So notice that our dynamic matching is a first period matching and a contingent matching plan. So we're going to call a dynamic matching stable as long as the contingent matching plan assigns a stable matching in the second period. Notice that the second period is simply a static matching market. So I can simply assign the group stability to the second period matchings, right? So a dynamic matching, I'm going to call a dynamic matching as dynamically group stable as long as there is no blocking coalitions for the second period matching for any possible first period matching. And anticipating what will happen in the second period, there's no blocking coalition in the first period either. And one important feature I should have told before, I should tell it right now, is that only contemporary blocking coalitions are available, are allowed, meaning that an agent who is not in the market at the time cannot be part of any blocking coalition. So meaning that the students who arrive to the market in the second period cannot be part of a blocking coalition in the first period. Or the students who match in the first period cannot be part of a blocking coalition in the second period.
I mean, but that's a bit weird, or not? If I match in the first period, I could block. Like, I guess I could sign a contract. Like, I could agree with some college, say, who is actually like enrolling a student in the second period to enroll me, right, instead, or not? That seems natural, no?
I'm sorry, can you repeat one? I couldn't really.
I was thinking, I mean, I guess if I understood correctly, you are saying that if I match in the first period, I cannot form a blocking pair with a partner who is matching in the second period. Is that what you said, or not?
No. If you match in the first period, you cannot be part of a blocking coalition of the second period. You can still be part of a blocking coalition in the first period.
I see.
Right.
I see. But I couldn't still go. I mean, and agree with the guy who is with the college that is like getting a partner in the second period to get me in the first period, right? That's still allowed.
That is allowed, yeah, because the colleges are the market from the very beginning, and
yes.
if you're in the first period as well.
I understand. That makes okay. I understand perfectly.
Yes, that is allowed. Exactly. All right, so this is actually pretty natural, because if you think about it, how I define a dynamic matching is analogous to a strategy profile. So the dynamic group stability is an analogy to subgame perfection. So for every first period matching, the second period matching has to be stable in the static setting, in a static fashion. Anticipating what will happen in the second period, there shouldn't be any deviation in the first period either. It's an analogy to the subgame perfection. Right? And it merges the dynamic stability introduced by Doval in her job market paper with the group stability, which is the standard solution concept of static man-to-one matching markets. All right, so if you don't have any more questions, perhaps I should continue. All right, so that's the solution concept. Let me try to tell you in this slide how I'm going to tackle this problem. So I start with a dynamic man-to-one matching market that is exogenously given to me. So I start in this part. And my question is, if I were to suppose that the market is static, that everybody arrived, say, in the second period, so there's no possible first period matching market, so it becomes immediately a static matching market, I will have sort of group stable matchings of that associated static matching markets, and I will have some dynamically group stable matchings of my original dynamic man-to-one matching market. So what are the relations between these two sets? I want to understand that. And the same question for this dimension as for this direction as well, where I'm given with a dynamic man-to-one matching market. Now I construct my related dynamic one-to-one matching market by splitting the colleges into seeds and constructing an artificial dynamic one-to-one matching market. So this dynamic one-to-one matching market will give me some dynamically stable matchings. And how are those related to the dynamically grouped stable matchings of my original matching market? So I'm trying to understand these two, but then I can go further and complete this graph by forming the related static one-to-one market as well, right? Simply just collapsing this related dynamic one-to-one market as if everybody arrived in the second period. So that sort of forms the static one-to-one matching market. Why do I do that? Because I know under responsive preferences, the set of stable matchings under this related one-to-one market and the related static man-to-one market are equivalent. We know that from before. And we also know that there are some work, and Laura shows that as long as agents are sufficiently patient, all statically stable matchings of one-to-one market will sustain to be dynamically stable as well in any dynamic one-to-one market. So we do know this one too. So as long as I form the link between dynamic many-to-one and dynamic one-to-one market, so that will allow me to sort of move directly to the static environment and form the link between static many-to-one and dynamic many-to-one environment as well. So that's how I'm going to tackle this problem. All right. So as I promised before, I'm going to give you this example, which I hope will convey the entire idea of the paper, because this example is crafted in such a way that every piece or every feature that I'm going to show is not the artifact of the example, but that it generalizes to be the result. So all the results that I will show will be in this example too. So let me try to go over this, this nice example that I believe will convey the idea. So let's suppose that we have two colleges, just like before, and 4 students this time. And each college is constrained with capacity 2. All right, let's talk about some preferences. The preferences of students are given in this table, and the way that you should read this table is the following. Student 1 prefers college 2 to college 1, but prefers college 1 to stay unmatched as well. And student 2, 3, and 4 prefers college 1 and college 2. But again, every single student prefers to be matched as opposed to staying unmatched. So that's how you should read this table. And the preferences will be strict. Okay, now let's define the preferences of colleges. This table shows the preferences of colleges over single students, right? So college 1, how you should read this table is, again, just like before. College 1 prefers student 1 the most, and then 2, then 3, and then the 4. And then, so it essentially means that college 1 is willing to match with anyone. So for college 2, the top student is student 2, then 3, and then 1, but student 4 is not even acceptable for college 2. Okay, but notice that the colleges will match sets of students. So this only defines the preferences over single students. So to complete the environment, we need to provide the preferences over sets of students as well. But we suppose that the colleges have responsive preferences from the very beginning. That essentially will imply ranking of some subsets of students, and for some subsets, it will not imply anything. For example, responsiveness implies that student 2 and 3 together is better than 2 and 4 for college 1, because 3 by himself is better than 4. All right. For the same reasoning, 3 by itself for college 2 is better than 3 and 4, because 4 is worse than null set anyways. All right. So with this, knowing that the colleges have responsive preferences, we are able to rank almost all subsets of students of size 2 for each of these colleges, except the ranking of student 1-4 versus 2-3 for college 1. Notice that 1-4 has a very good student and a very bad student, for relative to college 1's ranking, and 2-3 is sort of mediocre students. And either way of ranking is fine with responsive preferences. But it does not change the set of stable matchings of the static environment anyways. No matter how college one ranks these two, the set of stable matchings is fixed. But I will show you with this example that how college one ranks these two different subsets will change the nature of matchings that arises in a dynamic man-to-man matching market. Okay, so let's, you don't have to remember everything in this slide. I'm going to put all relevant information in this table, right? So all you need is to know that there are 4 students, 2 colleges, and the preferences of them. And also remember that the colleges have responsive preferences, all right? First, suppose that the environment is static. Let's take a look at the outcome of the static environment. In a static environment, a matching is simply the mapping of the students to the colleges or a null set, as long as a college is not mapped more than its capacity. All right, so that's simply what the matching is what the matching is in a static environment. Let's give an example of a matching here. The mapping of student 1-3 to college 1 and student 2 to college 2 simply defines a matching here. All right. Now let's talk about the group stable matchings of this environment. Remember that the group stability requires a matching to be immune to any blocking coalitions of any size. This, you should immediately see that this matching that I gave initially as an example is not a stable matching, because college 1 prefers student 2 to 3 and student 2 prefers college 1 to college 2. So college 1 and student 2 can block this match and get a better outcome for themselves, because by dropping student 3 and adding student 2, college 1 will get better off, and student 2 will get better off by enrolling to college 1, right? So then in this environment, we have a unique stable matching. In fact, in that unique stable matching, college 1 matches with student 2 and 3, and college 2 matches with student 1. So I'll show you very briefly why this is the stable matching and why it is the unique stable matching as well. So first of all, it's a stable matching because to see why it is a stable matching, notice that all matched students, student 1, 2, and 3, gets their top colleges. So no matched student would like to be part of any blocking coalition. But we also know from the rural hospital theorem that any unmatched agent of some stable matching will be unmatched in any stable matching. So student 4 will remain unmatched in every stable matching that we know. So then, no student will be able to part of a blocking coalition. So that essentially proves that this matching is a stable match. All right. It indeed is the unique stable matching because again, just like before, we know student 4 will be unmatched in every stable matching, but the students are, in this matching, students who are matched are getting their top choices. So it's a student optimal stable matching. Perhaps there is some other matching which makes colleges better off. So let's see how colleges can get better off. College 1 and college 2 have sort of reverse preferences regarding student 1 and student 2. Perhaps they would like to swap them and get better off, and that would be a stable matching, perhaps. But it's not, that's not going to happen because they can swap it, but then college 2 cannot commit not to poach student 1 back because it still has someone extra capacity. So that's why such a swap will not be sustained as a stable matching. Same idea goes for swapping student 1 and 3 as well. So that's why there is not any other stable matching in this environment. College 1 receives this mediocre students, student 2 and 3, and college 2 matches with the worst option for itself, which is student 1, and the students get their top choices. Okay, that's the static environment. Now let's suppose the environment is dynamic. And we have 2 periods. Just to make things simple, suppose that every single student arrives to the market in the first period, which doesn't have to be the case, but just to make things simple, right? As long as student 4 is in the market, it doesn't really matter who is in the market in the first period. All I need is student 4 to be in the market in the first period. Again, to keep things simple, let's say that everybody is in the market from the first period. All right. Now I'm going to construct a dynamically group stable matching under which that the colleges will get strictly better off. To do so, a dynamic matching, remember, is a first period matching and a contingent matching plan. So I'm going to start constructing the contingent matching plan first. which needs to be stable in the static fashion. But it's easy to do so because I can just fix this contingent matching plan to a college proposing deferred acceptance. I know that it's a stable matching algorithm, which by construction will sort of give me a stable matching in the second period for any possible first period matching, which kind of fixes half of my construction, which kind of finishes half of my construction. Now I need to construct the first period matching as well, under which there's no first period blocking coalition to that match. But that will be simple as well. Suppose that college 1 matches with student 4 in the first period. Okay. When college 1 matches with student 4 in the first period, we move to the second period, and in the second period now student 4 is not available anymore. And college 1 now joins the market, the second period market, with 1 capacity now, because 1 has been filled with student 4 in the first period. So in the second period now, college proposing deferred acceptance will be applied, and colleges will propose to their top choices up to their capacity. In this case, college 1 will propose to student 1, and college 2 will propose to student 2 and 3. And as you can see, there's no conflict about whom they propose. So they agree on their top choices now. And then that will be basically the outcome of the second period, where college 1 matches with with student 1, and college 2 matches with student 2 and 3. And that will be the college optimal stable matching of the second period, which we received by applying college proposing deferred acceptance. Okay, so overall, now college 1 receives student 1 and 4, and college 2 receives student 2 and 3, and both colleges get strictly better off. Right? I should have mentioned this before. It has been a long time now, but there is no per period payoff. Everybody only cares about their ultimate match. Okay, so matching with a partner in the first or in the second period does not change the payoff for neither colleges nor students. Okay, so this is a dynamically group stable matching, and I will prove in a couple of minutes now why this is dynamically group stable matching. Let me do that in a second. So simply, this matching is in the first period, college 1 matches with student 4. In the second period, college optimal, college proposing deferred acceptance is in use, right? So by construction, there is no second period blocking coalition to this dynamic matching, because college proposing DA is a stable matching algorithm, right? In the first period, on the other hand, potentially there could be some blocking coalitions, but let's check that. But notice that in the first period, college 2 wouldn't like to be part of any blocking coalition, because college 2 is already getting its top choices anyways. So with any blocking coalition, college 2, there's no way that college 2 can get strictly better off. That's the top that they can get. It can get, right? Let's look at what college 1 can do. Notice that in the first period, college 1 is matching with the worst student for itself. There is 2 and 3 is available in the first period, and they are preferred to student 4. So let's say that college 1 drops student 4 in the first period and picks student 2 instead. So when that happens now, in the second period, now student 2 is not available, and college 1 again joins the second period matching market with capacity 1, and college 2 again joins with capacity 2, and college proposing DA is going to imply that now college 1 proposes to student 1, and college 2 proposes to student 3 and 1. Now they have a conflict. So when that is the case, the student 1 is going to get to pick its top choice, which is college 2, right? So this deviation is going to move student 1 from college 1 to college 2. So overall, then college 1 is going to be matched with student 2 and 3 again, and college 2 is going to match with student 1, which was the outcome of the static environment. And this is not a profitable deviation by college 1. And the same idea goes if college 1 were to drop student 4 and get student 3 instead. So any deviation that college 1 would like to do in the first period will move student 1 from college 1 to college 2, which college 1 doesn't like to do so. All right. So the other possible deviation would be that they break the match and there's no first period matching at all. Then again, simply the outcome will be the stable matching of the static environment, which again is not a good thing, neither for college 1 nor for student 4. Okay, so then there's no profitable deviation in the first period either, which essentially proves that this dynamic matching that I have constructed here is a dynamically group stable matching in this environment. And let's take a look at a couple of features of this example. With this dynamic matching, college 1 receives student 1 and 4, but in the static environment, it was getting student 2 and 3. So college 1 prefers this sequential matching, dynamic matching, as opposed to static matching. And similarly, college 2 with this dynamic matching receives student 2 and 3, but in the static setting, it was getting student 1. So college 2 also prefers this sequential matching, this dynamic matching, to the static matching. Okay, let's try to see what really is happening here. When college 1 actually commits to match with student 4, it sort of implies a credible commitment in the subsequent matching market, which essentially says that college 1 and college 2 will not go after their top students. They're not going to try to poach students from each other. So by matching with student 4 in the first period, college 1 sort of commits not to go after students 2 and 3 in the second period, which frees up student 2 and 3, but then that in return sort of frees up student 1 for college 1, so they get to swap students in the second period, swap students at the top in the second period. So overall, this makes college 1 better off, and college 2 obviously gets better off as well, and this essentially leads to a better outcome for the colleges, this sequential matching. Okay, but notice
Ahmet,
that yes.
Yes, just have a question. I mean, I understand that in the US, like colleges typically go after the very good students early in the process, or is that correct or not?
I will actually show you that the early admitted students, there's a data that shows that early admitted students show inferior qualities as opposed to the students who are admitted in the subsequent matching market. And since the matching is dynamic in college, there's no way to sort of understand.
I see. But I guess that in that case, you also have something like risk aversion and uncertainties playing a role in those early matches, or not?
I'm not sure, actually. But it, so all I'm kind of saying with this example, with the results as well. So there are some reasons why colleges do early admissions in the US. One reason is that they would like to screen the students who do not need financial aid, or screen the students whose top choice is that particular college. I am providing some extra channel here why that colleges might be doing early admissions, because there has been early admissions in the US for more than 100 years by now, with different rules and etc. Somehow colleges do not really abandon that at all, at least the most selected ones.
Okay, I see. And
now there is some data that shows that the early admitted students somehow show lower qualities in several measures as opposed to the students who are admitted in the regular admissions period. So this result sort of highlights some of these empirical evidences, but I'm not really taking any stand on whether that is really the reason why colleges do that or not.
Okay. Okay, thanks.
Sure. Obviously, this behavior, relies on the fact that there's a limited capacity for the colleges here, right? So then there is this immediate result, which essentially is the following: if there were no capacity constraint for neither of the colleges, in such a commitment of the first period would not sort of imply any commitment of the second period as well. So this manipulation behavior does not arise in those environments. So the first sort of immediate result is that if the colleges are not restricted by some capacity, then it doesn't really matter whether the matchings take place sequentially or simultaneously. The outcome would be the same anyways. We can just pretend as if the market is static, and whatever we get there would be the outcome of a sequential matching in such market as well. Well, this is not really very interesting, but at least the capacity is sort of observable, is an observable characteristics, right? The primary case of interest is actually when the capacity constraint is binding, because that will allow for this strategic manipulation to arise, right? So I will now provide conditions under which, even though colleges might have colleges might be constrained with some capacity, this manipulation does not always arise, and I will show you conditions under which it does not. So let me go back to our example and give you some more features of the examples regarding the preferences. Notice in our example that regarding student 1 and 2, college 1 and college 2 had sort of reversed preferences. Let me just remind you briefly. When it comes to comparing student 1 and 2, college 1 were to prefer student 1 to student 2, but then student 1 prefers college 2 to college 1. And college 1, again, comparing student 1 and 2, college 2 prefers student 2 to student 1, right? But student 2 prefers college 1 to college 2. So this is, as you can see, this forms a preference cycle. Sometimes in the literature, it's called a simultaneous cycle. Sometimes it's called preference cycle, which I call a preference cycle here. But if the preferences would not exhibit such a cycle, strategic manipulation would not really arise, because matching with an inferior student early on will not really lead to swapping some students at the top in the subsequent matching market if the preferences do not exhibit such cycles. Okay, so the first result essentially is that if the preferences are acyclic, meaning that there's no preference cycle, then the set of dynamically group stable matchings is equivalent to the group stable matchings of the associated static many-to-one matching market. And that is the case for the associated dynamic one-to-one matching market as well. But the first part is more important because it essentially says that as long as the preferences are somewhat aligned, let's say, it doesn't form any cycles, then the dynamics do not play any role at all. And it's a strong result because no matter what the arrivals are, it doesn't matter who is in the market in the first period or not. No matter what the arrivals, as long as the preferences are somewhat aligned, then dynamics do not play any role at all. So we can pretend as if the market is static and look at the outcome of an associated static matching market, and that will be fine. Right? And just like I was telling before, the intuition is that the matching with an inferior student early on will not, help the colleges to swap students and get better off, because their preferences about the students or the students' preferences about the colleges are somewhat aligned. So there was no need to do this inferior matching in the earlier period at all, anyways. All right. So these acyclic preferences, there's a commonly observable class of preferences falls into these acyclic preferences, basically. So if one side of the market has homogeneous preferences, this forms acyclic preferences. So this result carries over the case where one side of the market has homogeneous preferences. In fact, I'm going to actually talk about, let me just skip this, and I'm going to talk about these homogeneous preferences and the role of cyclic preferences in real life applications, looking at college admissions in 2 different countries. So I'm going to talk about college admissions in Turkey versus the college admissions in US. So there's nothing really special about Turkey, but besides the fact that the preferences of colleges are expected to be homogeneous for the following reason. So the college admissions in the US is a static and centralized matching market. And it has been so for a long time by now, and there's no attempt to change it from this attempt to change the system from the colleges, neither from the colleges nor from the students anyways, for a long time by now. The center that assigns the matchings is called Measuring, Selection, and Placement Center. So the process is the following. So every single student, up to 2 million, I guess nowadays, take a test that is equivalent to SAT, and together with the GPA from their high school and some other measures perhaps, and this SAT score, some weighted average of all these measures, assigns some particular point to every single student, And given that particular point, every single student is ranked from 1 up to whatever million, however many people are taking that test. So, so that is the only relevant information that colleges have about the students. So then, you would expect that the college's preferences over the students is just identical to this, the rankings of the students from the very beginning until the last one. All right. So then, colleges basically have homogeneous preferences over the students, but there's no reason why students should have homogeneous preferences over colleges anyways. But it doesn't really matter. As long as one side has homogeneous preferences, this is going to give me an environment where there is no preference cycles. And based on my result, it shows that the dynamic, even if the matchings were to take place sequentially in a dynamic fashion, the outcome wouldn't change anyways. So perhaps this is one reason why there is no really attempt to change this static matching into sequential matching in Turkey for a long time right now. But things are different for the college admissions in the US. It's a dynamic matching environment, and it's a decentralized matching market. So every single college has various sources of information about the students, interviews, essays, some of them has alumni, parents, and many others, right? So every single college potentially has different sources of information. Even if they do have same information, colleges do not necessarily give same weight to the same measures, let's say. Yeah. So then, this potentially leads to a situation where colleges might rank some students in a different way. All right. And there's no reason, again, why students should have aligned preferences over colleges either. So the college admission system can exhibit preference cycles. And again, based on my result, when there are preference cycles, colleges can benefit from sequential matching as opposed to static matching. And perhaps this is one of the many reasons why colleges never really abandon these early admissions, but keep it there with different rules over time. Because the dynamics can make a difference in favor of colleges.
Ahmet, you have 5 more minutes.
Okay, I am fairly sure that I can finish these 5 slides in 5 more minutes. All right. Okay, so this is the first result. Under acyclic preferences, let me just wrap it up. Under acyclic preferences, dynamics really do not play any role at all. The set of stable matchings of the static market is equivalent to the set of group stable matchings of dynamic group stable matchings of the original market. So that's good to know. But what if the preferences were to include cycles, let's say? Then does that mean the dynamics will matter? Not necessarily. Or does that mean that the result, the outcome of a static market will fail to be dynamically stable? That's not necessarily the case. Again, let's just go back to our example and look at the preferences of college one there a little more in depth. I actually mentioned this before. Notice that college one prefers students in this following way. Student one is the best, student four is the worst, and 2 and 3 is in the middle. Responsive preferences, as I was telling before, does not really imply anything about the ranking of these 2 subsets. Either way of ranking is fine, is consistent with responsive preferences, but no matter how this is ranked, does not change the set of stable matchings in the static environment, but it plays a crucial role in the dynamic environment, right? College one. We suppose that college one prefers this student 1 and 4, like this extreme set of students, the good ones and bad ones, to the mediocre students, right? When that is the case, in our example, we have seen that college one is going to engage in this strategic manipulation and get benefit from this sequential matching. But if this preference of college one regarding these 2 sets were reversed, then the college one wouldn't really engage in this strategic manipulation and would be fine with the outcome of the static environment. So it turns out that this is not just the artifact of an example. It essentially is the case for a general setting as well. So for that, now I define a notion of average and extreme preferences, which is akin to the notion of mean preserving spread, let's say. So take any 2 subsets of students with the equal cardinality, where one has more extreme students and good and bad students, and the other has mediocre students. So the comparison of these two is not really implied by this responsive preferences. Now I'm going to classify this a college as if it has extreme versus average preferences, depending on how a college ranks these two different subsets. If a college prefers mediocre students to the extreme ones, then I'm going to call that college has average preferences. If it is the other way around, I'm going to call that that college has extreme preferences. Okay, so the next result essentially says that if the colleges have average preferences as opposed on top of having responsive preferences, then it turns out that the group stable matchings of the static environment induces a dynamically group stable matching of any dynamic many-to-one matching environment as well, no matter what their rivals are. So this essentially tells that, by looking at the static version of the original dynamic many-to-one matching market, we're still fine. So whatever the static market predicts will be an outcome of the dynamic environment as well. But there's a caveat there, which essentially is the following. By looking at the static version, we're actually losing some. So there are some more dynamically group stable matchings which we cannot really, which is not really group stable in the static version of the market. So we are losing those ones. But this result essentially tells that with a careful choice of matching algorithm in a static setting, we can prevent some of the some unravelings in some matching markets. Okay, the intuition is the following. Now, in our example, college 1 sort of loses in the short run by matching with student 4, but gains in the long run by matching with student 1, and ends up with a more spread out set of students. But if the college wouldn't like this more spread out set of students to a less spread out one, then this college 1 wouldn't do this in the first place anyways. Okay, so notice that there's an asymmetry between the earlier result and this one. In the acyclic preferences result, we had the equivalence between the stable matchings in a static environment and the dynamically group stable matchings of the dynamic one-to-one matching market, right? We weren't losing anything by looking at the static environment. But here, now the set of dynamic group stable matchings is a superset of the set of stable matchings of associated static matching market. I will be happy to talk about the asymmetry between those two results, but I should continue for the interest of time. Okay, so do I have 1 or 2 minutes, or did I pass the time already?
No, it's okay. You have 2 minutes. It's okay.
Okay, all right. All right. So far I have introduced. I have sort of provided conditions under which we can rely on the results of the static market. But what if we cannot? So what should we expect if the outcome of the static market is not dynamically group stable at all? Then, in our example, remember that the static matching is not really the dynamically group stable matching, and who benefits from this matching is student 4, who was ranked the lowest by college 1 and not even acceptable by college 2 anyway. So student 4, in some sense, is the worst student in the environment. So that, it turns out, it's not really artifact of the example. Again, the students who are matched in the earlier periods are ranked lower than the students who are matched in the subsequent matching market. That's the second point. And not only that, those students who are matched in the first period are actually ranked even lower than the students that particular college could have matched in a static environment as well. So they are sort of worse than the partners, the students that will be admitted in the second period, but they're also worse than what this college would have gotten in the static environment as well. Well, this is good because, like I was telling before, we have a similar trend in a similar sort of pattern in the US admission system as well. The students who are admitted early on show lower qualities in various measures, such as the SAT score, extracurricular records, and etc., as compared to the students who are admitted in the regular admissions period. Right. So this result sort of sheds, highlights this evidence that we observe in US college admission system as well. Yeah, I will be happy to talk about indigenous arrivals with anyone who is interested, perhaps off the line, but let me try to conclude now. So in this paper, I study man-to-one matching markets in a dynamic framework and point to a novel strategic behavior that pertains only to dynamic man-to-one matching markets. And I provide sort of conditions or instances under which dynamics do not play any role, and or at least we can rely on the results of the static matching market. And if we cannot do so, I provide a property of the sequential matching that arises in markets where we cannot really simplify the market to neither static man-to-one nor in dynamic one-to-one matching markets. And the second part, I study the endogenous arrivals. I sort of relax the assumption of exogenous arrivals and study the unraveling incentives of commonly used matching mechanisms, which unfortunately that I wasn't able to go over for the time restrictions. Well, I appreciate. Thank you very much for listening. If I passed the time a little bit, please forgive me. I must have been quite sort of excited about it, and I just couldn't stop myself, I think.
No, thank you, Ahmet. Thank you. Thanks a lot. Are there any questions?
Oh, I just have one question. How natural is the assumption of extreme preferences? I was trying to think. It seems to me that, what would the college want? Would like a more homogeneous kind of group of students, or like a very good student and a very like so-so student? It seems to me that homogeneity is important, no? I mentioned it because this is very important for the connection between static stability and dynamic stability.
Yes, that's true. That's true. Well, so the way I look at it is the following. I'm not sure how realistic for the colleges, but so to understand it, perhaps it's useful to think about college admissions and the medical residency matching, for example. Okay, medical residency matching market is a static market, and what is it? And although there are some early matchings that happens between the interns and the hospitals, it's very rare. So it's a successful market where there's not much unraveling. But the college admissions is sort of a dynamic matching market. The colleges, do they really care about how bad are the bad students, or do they really care more about how good are the good? I don't know how to say it. So the bad student in a college cannot really ruin the reputation of the college, but a really good one can increase the reputation of a college quite a bit, right? But that's not the case for hospitals. So a bad doctor, bad intern can really ruin the reputation of a hospital, as opposed to a very good doctor increasing its reputation. So the way I think is that the hospitals might be inclined to have average preferences, but the colleges could have more extreme students because they care about the really good ones. The bad ones, okay, that's a risk. I take it. If they, if they turn out to be good over time, that's good. If not, I can always drop them over time, or it's not. So that's how I think about it. But I think this is, it's a new class of preference that I introduced in this paper. I think it will be sort of useful to understand, in what markets we might observe one or the other. But that's how I think about extreme and average preferences in these two different markets. Does that?
Thanks. Thanks.
Okay, so any questions? Bonnie, no? Okay, so thank you, Ahmet, and thanks for the presentation. Actually, I have a few more, but maybe I will write to you about that. Okay. Okay.
Yeah, that would be great. Thank you very much, all. I really appreciated this.
Thank you. Thanks to all participants. Bye bye.
Teşekkür ederim professors.
Teşekkürler Ricardo. Teşekkürler.
All right. Thank you very much.
Bye bye.